This is Calculus 1 video lecture number 4 on the precise definition of a limit. So to start our discussion, we're going to look at a simple linear function f of x equals 4x minus 5, and it's graphed here, just a portion of it in the first quadrant. Now, we know from the limit laws that if we want to find the limit as x approaches 3 of f of x, I can use the direct substitution property. So I can just substitute in 3 for x into the function and evaluate the limit. So 4 times 3, that's going to be 12 minus 5, and this limit's going to be 7. And you can confirm this graphically as you approach x equals 3 from either the right or the left. F of x, my function, approaches 7. And in that case, the limit is equal to the function value. So now I have a question for you. How close to 3 does x have to be so that f of x, or y, differs from 7 by less than 0.1? So basically what I'm saying is I want to be able to go up to 7.1 or down to 6.9 on the graph. That's the amount of wiggle room I'm allowed in the y direction. And I want to know, how close does x need to be to 3? So how much wiggle room do I get in the x direction to stay within 7.1 or 6.9? All right, so here's how we're going to look at this question. First of all, the distance from x to 3, remember it could be to the left or to the right of 3, that's going to be represented or given by the absolute value of x minus 3. And similarly, the distance from f of x to 7 is going to be the absolute value of f of x minus 7. So what we're trying to do is find delta, that's lowercase delta, such that the following holds. So we're given the fact that we want the distance from our function to 7 to be less than 0.1. If x minus 3, the distance from x to 3, is less than delta, some delta. Well, here's the process. We start with, what am I restricted to doing? Well, f of x minus 7 has to be less than 0.1, right? We want to be no more than 7.1 or at 6.9 on the graph. In this particular case, f of x is equal to 4x minus 5, so I'm going to substitute that in for f of x. So I have 4x minus 5 minus 7 is going to be less than 0.1, right? I want that distance, that difference, to be less than 0.1. Okay, I can clean up a little bit, combine some like terms. So I have absolute value of 4x minus 12 is less than 0.1. And I can factor out a 4 from both those terms. So let's see here, 4 times absolute value of x minus 3 is less than 0.1. And oh my goodness, there's that absolute value of x minus 3 popping back up. That's the difference, or the distance, from x to 3. So if I divide by 4, now I know that the distance from x to 3 has to be less than 0.1 divided by 4, which is 0.025. So my answer is that I need to let delta equal 0.025. All right, let's see if we can confirm this. Let's check it on our graph, okay? So we know that the limit as x approaches 3 of f of x is equal to 7. That's shown there. And remember, we wanted to be able to go up to 7.1 and then down to 6.9. So say this is 7.1, this is 6.9. Okay, and they hit the graph there. Well, if I trace those points down, then they should correspond with, you guessed it, this value right here should be 3 plus delta, so 3.025. And then the value on the other side is going to be 3 minus delta, which would be 2.975. So basically, you're given the wiggle room in the y direction, right? 0.1 up or 0.1 down. That was our epsilon. And then you have to find delta, which is the wiggle room in the x direction. In this case, delta was 0.025. And the good thing is it goes in alphabetical order, right? Delta represents the distance from x, epsilon represents the distance from f of x or y, and delta comes before epsilon in the Greek alphabet, just like x comes before y. So you're good to go. Okay, so we can summarize that graphically we've confirmed if x is within a distance of 0.025 from 3, then f of x will be within 0.1 from 7. But who's to say we had to stick with 0.1? What if I wanted to change it to 0.01? Could I do that? What would be different? So say instead of 0.1, I made this difference 0.01, so I could only go up to 7.01 or 6.99. Could I still find a delta? Well, sure, it would just be smaller, right? And so this is how we come up with a more precise definition of a limit. 0.1 was chosen arbitrarily, and we're going to use the Greek letter epsilon to denote any small positive number, and that's going to denote the distance from f of x. Okay, so epsilon represents the distance from f of x, delta represents the distance from x. And here's our precise definition of a limit. So we say that the limit as x approaches a of f of x is equal to L if for every epsilon greater than 0, there is a delta greater than 0, such that if, and this is the distance from x to a is less than delta, then the distance from f of x to L is less than epsilon. And I'll show you here with arbitrary notation how that would work. So here's the limit L. And then you're going to be given some epsilon. So say you come up here, this is going to be 7 plus epsilon, or maybe down to here, that's 7 minus epsilon. The idea is you take this back to the graph, That's the wiggle room that you're allowed in the y direction. So this is the wiggle room that you're allowed. And then now you want to figure out, okay, how much wiggle room do I get in the x direction to stay within that epsilon band? And whatever that distance is, there's your delta. So there's your 3 plus delta, and then on the other side, that's your 3 minus delta. Okay. Good. Now let's look at a few more examples. And we're just going to do very basic examples in this lesson. First one, use the given graph of f to find a number delta such that if the distance that x is from 3 is less than delta, then the distance from f of x to 2 is less than epsilon. All right, so look here. I know the epsilon in this case is 0.5. They're telling me from 2 we can go up to 2.5 or down to 1.5. That's basically my epsilon. 0.5 here, 0.5 here. Now I want to know how much wiggle room do I get in the x direction to stay within 2.5 to 1.5. And you have to stay on the graph. Okay, you're staying on the graph. All right, well, let's see here. If we were at 2.6, the distance from 2.6 to 3 is equal to 0.4. And if we go all the way to 3.8, the distance from 3.8 to 3 is going to be 0.8. So in this case, it's not symmetric on both sides the way it was with the linear function that we looked at earlier, right? Now what we need to do is choose the smaller value to guarantee that we're in the window. Why is that? Well, if I chose 0.8, look, I'd have a problem. Because if I went 0.8 to the left of 3, that would take me to 2.2. And why is that so bad? Because if you take 2.2 to the graph, now you're out of bounds. Remember, the lowest we can go is 1.5. So that's why when you don't have a symmetric distance on both sides of x, you have to always choose the smaller. So how do you write it up? Don't worry, we've got a slick way of doing this in math. We say delta is the minimum of those two distances, 0.4 or 0.8, which is going to be 0.4. So you choose delta to be 0.4, and then in that case, you're only going to allow yourself to go up to 3.4, but that's fine because you're still less than 0.5 away from 2. Okay, you're playing it safe, basically. We must play it safe. All right, very good. Now let's get into some actual proofs. Okay, so prove using the delta-epsilon definition of a limit. So we have the limit as x approaches negative 1.5 of 9 minus 4x squared over 3 plus 2x, and this is equal to 6. So before you get started, make sure that you have memorized what the precise definition of a limit is, and then identify exactly all the parts that are going on here. So negative 1.5, that's a. This expression here, this is your function. This is f of x. And 6 is the limit. Okay, and then just follow this example. Use it as your template anytime you're using the precise definition to prove a limit. Okay, so you start off, you have to write let epsilon be greater than 0. That has to be there. We need to find, you can just list this all out verbatim, okay? So we need to find delta greater than 0 such that whenever, and then you have the distance that x is from a. So in this case, that's going to be x minus, remember a is negative 1.5, is less than delta, then the distance of f of x to L, so f of x minus 6 is less than epsilon. Okay, so copy that first statement anytime you do one of these proofs. You're just going to replace with the appropriate A and L to start off with. Okay, then you kind of work them backwards. So you start off with f of x minus 6 has to be less than epsilon, right? You're only allowed a certain amount of wiggle room in the y direction. And then now you come and start plugging in. Okay, so in this particular case, f of x is 9 minus 4x squared over 3 plus 2x. So that minus 6 is less than epsilon. And remember, your goal is to find delta. So you want to get x minus a, so in this case, x plus 1.5, to appear as you manipulate this stuff here. Okay? All right, let's see here. Can we clean this up? Yeah, factors, the numerator factors. So I'm going to have, it's a difference of squares, right? So 3 minus 2x times 3 plus 2x over 3 plus 2x minus 6. That's less than epsilon. Cancel, cancel. And then here, you're just going to have to be a little careful. You have the absolute value 3 minus 2x minus 6 is less than epsilon. Okay, so if I combine like terms, now I'm going to have negative 2x minus 3 is less than epsilon. And remember, I'm trying to get x plus 1.5 to appear. And I notice I can factor out a negative 2, but do that carefully. So if I take out a negative 2, then I have x plus 3 halves as the other factor inside absolute value. That's less than epsilon. And then you might notice we're almost there. So if you break it up, you have absolute value of negative 2 times the absolute value of x. I'm going to put plus 1.5 so it looks like how they had a in the problem. Okay, typically we don't use decimals, but since that's how the problem was written, I'm switching. And then absolute value of -2 is just 2. So I can divide by it. So this means 2 times the absolute value of x plus 1.5 is less than epsilon. And then dividing by 2, then I have x plus 1.5 is less than epsilon over 2. So what does that mean? That's my delta, remember? X minus -1.5, that difference, the absolute value of that is less than delta. So I need to choose delta to equal epsilon over 2. So here's the idea. If someone said, hey, epsilon is equal to 0.5, you would say, oh, no problem. Then that means delta is half of that, 0.5 divided by 2.25. And then if they said, no, I changed my mind, now epsilon's 0.1, okay, no big deal. I know delta has to be epsilon over 2, so 0.1 divided by 2, 0.05. So epsilon can be made as small as you like, and you just will take your delta to be half of that in order to stay within that epsilon band, to stay, that's your wiggle room that you're allowed in the x direction. Okay, we'll do one more. There's obviously lots and lots of cases where you can show the limit doesn't exist using this method. Infinite limits are dealt with differently, but we're only going to stick to just this basic straightforward case where it conveniently works out like this to just factor out a constant and then wham bam, there's x minus a that appears. Okay, we won't do anything too wild in this class. All right, example 3, bonus example. You weren't expecting it, huh? Okay, so again, prove using the delta epsilon definition of a limit. And they're giving us that we want to find the limit. Prove this as x approaches -6 of 5 plus 2/3 x equals 1. Okay, so before you get going, label everybody. This is A, that's f of x, and that's L. Okay, now this example is pretty straightforward, so why don't you take a second, pause the video, look at the previous example and see if you can just copy that rubric, copy that outline, and apply it with this function, this limit, this a. Okay, I'll give you a minute to do that. Okay, how did you do? Let's go through the solution together. So you start off by writing let epsilon be greater than 0. If you forget that, it's -1. Then we need to find delta greater than 0 such that, you know, you can abbreviate such that. I didn't make it up, that's real. Such that whenever x minus a, so that's x minus -6, is less than delta, then absolute value of f of x minus L, which is 1, is less than epsilon. Do you have that statement on your paper? You need to have that. Okay, then you start always with f of x minus 1 is less than epsilon. Then you replace f of x with the function you have there. In this case, that's 5 plus 2/3 x minus 1 is less than epsilon. And if you want to remind yourself, what's your goal? I'm trying to have x minus a pop back up in there somewhere, because then I have my delta. So I want to see x plus 6 in the expression somewhere. Okay, we'll get there, we'll get there. So now I have absolute value of 2/3 x plus 4. That's less than epsilon. Let's try factoring. It worked so great last time. So I'm going to take out a 2/3. Okay, if I factor out 2/3 from 4, that's the same as multiplying by 3/2, which is going to give me plus 6. Oh, there we go. Woohoo. If I take out absolute value of 2/3, it's just 2/3. I still have absolute value on x plus 6, which means absolute value of x plus 6 is less than 3/2 times epsilon. So what does that tell me? I'm done. I need to choose delta to be 3/2 epsilon. Okay, so for my class, this is the template that I want you to follow, and we'll only do really straightforward introductory style proofs where you only have to factor out a constant and then bam, you can find delta. There's a lot more, proof techniques for more complicated functions, but we won't get into that in this class. Also, if you have a different instructor and they have you set up the template differently, make sure you follow their outline, their directions, because there are a couple styles or approaches to doing this. So just do whatever it takes to make your teacher happy, but still understand the material and what it's saying. And that concludes the lesson on the precise definition of a limit. Don't forget to give it a thumbs up, subscribe if you haven't, and stay tuned. We've got so many more calculations.